Okay, so there was a gap of one lecture last time, right? Anyway, uh, so we were looking at recurrence relations, right? We finished recurrence relations. Now, why we study recurrence relation? Now you will know that whenever we study bunch of algorithms and we want to study their complexity, so normally when we want to compute the complexity as a function of n, it turns out that it satisfies a recurrence relation. Okay, so that's why for us it is very important that we should study recurrence relation. So we know about the recurrence relation now. Now I will show you with a couple of examples that if you take a algorithm, look at the recurrence relation arising from it, and then try to find the complexity in terms of big O notation. Okay, so that big O of notation is very, very important. So that allows us to compare various things among the algorithms. So I think after this, so basically there is one main theorem. Probably I will skip the proofs. Although I know that I have done in the last time these proofs, but I can look at how these things are applied, and then we look at graph theory. Towards the end, most likely we will be able to start graph theory, certain basic things. So graph theory is also very, very important topic. So let us start with this. Essentially, master theorem is a very important theorem. And I think in your design and analysis of algorithm codes, normally which comes in at third year or maybe second year, I think you will probably know more about these things. Okay. So if I look at binary search, if I look at binary search algorithm, you remember we divide things into half and then again half and half, right? And then we do. So there actually, if you look at number of comparisons in a search sequence of size n, and suppose this number is f of n, then you will observe that when n is even, I can assume that n is even for simplicity. Otherwise, you have to use ceiling or floor, whatever. So f of n is equal to f of n by 2 plus 2. This two constant term basically needed to implement the reduction. So one to determine which half of the list to use. There are two to determine which half to use, right? And to determine if any term of the list remain. So essentially, this is the key thing. F of n is equal to f of n by 2 plus 2. So this is a kind of recurrence relation that we want to solve, right? Of course, this is a constant, so which is okay. But this function of n is an important thing. Okay. So let me write down a most general thing that you can get while doing these things. The most general equation will be something like this. F of n is equal to a times f of n by b plus g of n. So what is happening? So we wanted to search a list of n objects. We divided it into half. So what we are doing is divide and conquer, right? So we need to divide half, 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 and then you combine the problems, right? The solution basically in each step. Okay. So basically this is this term here for extra operations, for combining the solution. Okay, so this is nothing but divide and conquer recurrence relation. You can call it as divide and conquer recurrence relation. Most general thing, right? Whatever we saw in binary search, this could be the most general thing that we can happen. Now, actually, how do we simplify it or solve it? Suppose I'm making such certain assumptions. Suppose n is divisible by b. Okay, so let n is of the form b raised to power k, where k is a positive integer. Okay, then f of n can be written as a of f of nb, n by b plus gn, right? And I can again use the same recurrence here, f of n by, I can use the same equation here again. So what you will get? You will get something like a square f of n of b n by b square plus a times g of n by b plus g of n. Okay, I have used the same equation again in that recurrence. And we can continue like this. So we will get something like a cube f of n by b cube plus a square g of n by b square plus a times g of n by b plus g of n. And so basically, so taking that recurrence relation and I'm just iterating it, right? So we get, this is the most general thing. So we iterate it, we get a square. So here we are using the same recurrence relation again. We get something like this. Again, use the same recurrence relation, you get something like this, and keep on continuing this way, right? So what you are going to get, the most general thing is something like this. F of n is equal to, after certain number of steps, a raised to power k, f of n by b raised to power k plus summation j is equal to 0 to k minus 1, a raised to power j, g of n divided by b raised to power j. Okay. Now, since n by b raised to power k is 1, our assumption, this simplifies. F of n is equal to a raised to power k, f of 1 plus summation j is equal to 0 to k minus 1, a raised to power j times g of n divided by b raised to power j. Okay, so this is because we have assumed that n is equal to b raised to power k, right? So n divided by b raised to power k is equal to 1. So we have something like this. Now, one can prove from this expression that Fn is big O of what value? So I think I can just mention the result. It is kind of this theorem. We we assume that f is a increasing function, and which satisfies the relation that f of n is equal to a times f of n by b plus c. Okay, where n is where b divides n, actually n is divisible by b, a is greater or equal to b is greater than 1, and c is a positive real number, then we can say that f of n is equal to big O of n raised to power log of b base a if a is greater than 1, and big O of log of n if a is equal to 1. Okay. So this result is there. Of course, I think we have done this proof last year, but anyway, I'll skip this time basically. So you should know the result. So if we have the expression like this, we can arrive at this kind of stuff. Okay. So as an example, we can show you an example. Suppose f of n is equal to 5 times f of n by 2 plus 3 and we know that f of 1 is equal to 7. So if I ask you, anyway, we'll do the another one actually, sorry. Take f of n is equal to 2 times f of n by 2 plus 2. Okay, so then f of n is equal to big O of n raised to power log 2 using previous theorem, using this theorem. Okay, because f of n is equal to a times f of n by b plus c is a constant here. So b is 2 here, right? So this is the value, you know. Okay, and since b is equal to 2, actually this turns out to be big O of n. Okay, I'm going to mention most general theorem, which is known as master theorem. F is an increasing function, and the recurrence relation is f of n is equal to a times f of n by b plus c times n raised to power d. So previous theorem we had only c, now we have this multiplied by n raised to power d. And of course n is equal to b raised to power k, k is a positive integer, all these conditions are given, a is greater than or equal to 1, okay, and b is greater than 1. And of course c and d are positive real numbers including 0. In this case, f of n is equal to big O of n raised to power d if a is less than b raised to power d, big O of n raised to power d times log of n if a is equal to b raised to power d, and last case if a is greater than b raised to power d, it is big O of n raised to power log of b base a. This is a very important theorem. So we saw initially when this part was not there, and this is the most general result, you know. Of course, I'm skipping proof because I think proof you can look at some when you do more advanced course in algorithms. But anyway, you should know the theorem and you should know how to apply it. So f of n is big O of n raised to power d if a is less than b raised to power d, big O of n raised to power d times log n if a is equal to b raised to power d, and big O of n raised to power log b base a if a is greater than b raised to power d. Okay, so this is known as Master's theorem, very beautiful theorem. Of course, the proof is there, you know, just like in the previous case, but we are skipping the proof right now. So I think we can look at again an example. You might have seen matrix multiplication. So one can ask the complexity question, what is the best algorithm to multiply two matrices? Okay, so that is something is there. For multiplying two n by n matrices, the recurrence relation turns out to be f of n is equal to 7 of f of n by 2 plus 15 times n square by 4. Of course, n is given here. So then f of n is, by using this master theorem, big O of n raised to power log 7. So this is the complexity for multiplying two matrices, I think. Okay, I think that's all. So basically, essentially, there are two theorems which I mentioned, the master theorem. So whenever we are given expression like this, we know how to give you the complexity, right? Big O. I mean, you can simplify by computing log 7 here, you know, but okay. Okay, so I think this was all about complexity. Another interesting thing is now, in fact, the last thing, probably after that, because there were a couple of there will be a couple of classes left, so we'll be covering posets as well. So let us start another interesting topic, which is graphs. And I think there are many people in the campus who know graphs? How many of you know about graph? Anyone? Graph is very simple thing. It started from a river, right? Germany. There is 7 bridge problem that resulted in graph theory. So essentially, if I ask you, can you make this kind of picture? Without lifting your pencil, right? Can you make it? So it will be difficult, right? You immediately realize that there is a problem. So whenever we try to draw it, right? So basically, you have to either walk twice, right, on any path. That is the only way when you can draw this. So these kind of puzzles you might have done, but so similarly, there was a river in Germany where there were 7 bridge, and you have to go from one island to come back to the same island by walking through the bridge, so that you should not repeat the bridge twice, right? And what is the weight? And that was something which gave rise to this graph theory. So what people did, they looked at the actual scenario and they converted into picture like this: points and lines. There are a bunch of points, bunch of lines, and they are connected to each other. Okay, so obviously I think I gave you one problem about points, lines in my first lecture, if I remember, right? And I think you were not able to find a solution, so I gave you the solution as well, right? 7 lines, 7 points, all that kind of stuff. Anyway, so it's an interesting thing. So graphs are very, very common. I always say that graphs are nothing but a common sense, basically. So in general, graphs consisting of vertex set and edge set. Vertex set. Right? So basically, if vertex set is infinite, it is known as infinite graph. And when vertex set is finite, it is known as finite graph. So there are plenty of examples. For example, I think many problems you can look at in a natural way from graph theoretic point of view. For example, if you look at paper writing, right? So everybody who has published any paper or even not published any paper, you can find out what is known as Erdos number. Have you heard of Erdos number? Erdos number is a project by a mathematician. So they they construct graph. Like if you have written paper with me, so suppose I am Erdos, and if you have written paper with me, so your Erdos number will be 1. If somebody has written paper with you, that person will have Erdos number 2, and so on, right? So I am at the center. I'm Erdos, so I am at the center. So like that, you can find collaboration graph. So, who collaborate with whom, and you can make a graph out of it. Luckily, these things have certain interesting properties that most of the famous people in the world have very less Erdos number. Okay, so all these Nobel Prize winner, great scientists, right? They have a very small Erdos number, and since Erdos is no more, certainly your generation cannot have Erdos number 1, right? But you can have Erdos number 2 by collaborating with someone who has Erdos number 1. And optimal Erdos number, I can say now, is 2, basically, right? who is the best thing. I mean, because one, so let me show you. ADOS number project. So this is the graph you can see. I think this picture is on the Wikipedia. First, let me show you the graph actually on the Wikipedia. It's not there. From where they're getting pictures? This guy is Paul Ados. By the way, his research papers were coming even after his death. He's written around 1600 papers, okay, in the lifetime. And he used to have a bag, one or two clothes, and always traveling all over the globe, writing papers with any kind of person, you know, mathematician, computer scientist, electrical engineer, anyone, right? So that's why he has published a lot. So I think some famous people with, you see, can you see the list? These are some famous people. Niels Bohr, ADOS number 4, 5, 6, 7, all this, you know, all great people. I think Bill Gates has ADOS number 4, I guess. Right, so you can find this list. Chemistry, economics, he has published everywhere, you know. So anyone who has published anything will have a ADOS number, right? So normally the property is, you know, the ADOS number normally you will find with people with 11 or 12 at most, you know, doesn't go far. You know, most of the people will, you can classify under this 11, 12 or something like that, you know. So in fact, my ADOS number is 2. So I collaborated with someone who has worked with ADOS, you know. So anyway, so if you write a paper with me, your ADOS number will be 3. So that is there. So this is an interesting graph actually, you see. You can see that most of them, you know, 2, 3, 4, 5, and all these great people have less ADOS number. Okay. Even geology, philosophy, anywhere, you know, Sergey Brin, the person who started Google, ADOS number 3, right? So Sergey Brin from Google, ADOS number 3, you can see that, right? So you can try to find your ADOS number. So either ADOS number is finite or infinite. If you have never written any paper with anyone, it is infinite, right? If you have written paper with anyone in any area, it will be finite ADOS number. You can find out what is your ADOS number, right? It's an interesting thing. So basically, you can look at the graphs. I think these images should be visible. Yeah. Look at the graph. Oh, where is the graph? Strange. You can see the distribution. There is one person with ADOS number 0. ADOS number 1, there are 504%. ADOS number 2, 6,593 people are there in the world who have ADOS number 2. Okay. And then 3, 33,000. So 3 is there are more. It is difficult to go here, but here there is more, you know, 3, 4. And then you see there is a decrease thing, you know. ADOS number 13, there are only 5 people. It's kind of, you know, there's a kind of distribution you can observe, okay, in the data. Anyway, so this is something interesting. So basically you can make a graph, you know. Anyway, so I think this picture. I think somehow you can see the graph, right? This is a collaboration graph, right? Ardos is the center, and then you can, draw these lines. Complex graph, right? By the way, do you know that your internet has a graph structure as well? What is the name of the internet graph? It is known as bow tie structure, bow tie structure. So what happens? Certain pages are very well connected. They also follow this kind of property. Some pages are very well connected. So it is something like this, something. Those who are good, you can find them in one neighborhood, right? Those who are bad, you can find in one neighborhood. And this is true. So for example, this property holds even on network like Facebook. You can think of as a Facebook as a big graph. You can see that if there are fake profiles in the neighborhood, there are more fake profiles, right? So those which are connected to it. So this is something very common property, in terms of graphs. So bow tie structure is a very thing. You can draw graph in terms of flight maps, phone calls, whatever you want. You can do many things actually here. So now I can give you some definitions actually. Okay. So simple graph. So each edge connects two different vertices. Okay. So no two edges connect the same pair of vertices. Okay. No two edges. Okay. So this is a simple graph. Multi-graph, when graph has multiple edges. It has multiple edges. Okay. Connecting the same vertices. These are some common sense definitions. Okay. Loops, if you start from a vertex and connect it to itself, right? That is a loop, which is fine. You can talk about loop. Undirected graph, directed graph. Undirected graph when there is no direction, right? Directed graph we can talk about when there is a direction. Basically, you can draw like an arrow from one place to other place, right? Another one, arrow is there, right? Directed graph. So each edge has a start vertex and end vertex. Okay. So on. So there are some interesting things. By the way, just like this, just like ADOS number, you can also have. There is also known as Bacon number. I don't know whether you heard of Bacon number, or you can take any filmy actors or actress, and you can draw the graph. Who has worked with whom, right? That kind of graph. So Hollywood graph, right? Sorry, Bollywood graph and Hollywood graph, whatever you want to create. You can create something like that. Okay, so suppose G is a graph, so vertex set and edge set, right? So let me draw this picture here. A, B, C, D, F, G. This is a graph. How many vertex are there? 1, 2, 3, 4, 5, 6, 7 vertex are there, right? I can talk about what is known as degree of vertex. What is the degree here? 2. Two edges are connected. Degree here. What is degree here? 4. Here. 4. 1, 2, 3, 4. Here. 3. Here. 4. Here. And here. Very good. So, these are common sense, right? Degree of it. So such kind of vertex is known as isolated vertex, right? I mean, of course, it is isolated, right? Okay. By the way, graph theory has many interesting problems. There is a marriage theorem. I don't know whether you heard about it. Philip Hall marriage theorem. Okay. So let me give you handshaking theorem. Okay, handshaking theorem. Suppose G is equal to V comma E is an undirected graph. With E edges. Means cardinality of E is small e. Then 2 times E is equal to summation U belongs to V degree of U. So degree of U. So suppose graph is undirected and there are total number of E edges are there. E edges are there, right? 1, 2, 3, you can count how many edges are there. Then 2 times E is equal to, so if you compute the degree for each vertex and sum it over all vertex, you get 2 times number of edges. Can you tell me why? Because any two vertex are connected by one edge, right? So everything will give you twice, right? So basically when you sum, so this is 2 times number of edges equal to sum of all the degrees, right? It's a very straightforward thing. Okay. So this is handshaking theorem, okay? By the way, those people who are very good competitive programming or whatever programming, some very good in competitive programming and so on. For them, I can give you very difficult problem. When we say that two graphs are, so basically I want to find out for a given number of vertex, how many graphs are possible? If I say that n is equal to 1, only one vertex, how many graphs are possible? एक तो हो जाएगा, डॉट डाल दिया खाली, isolated vertex, that is one graph. Another could be vertex और उसके ऊपर एक loop लगा दिया, that is another graph. So what kind of question is that, whether simple graphs, how many? If I ask simple graphs, then there is only one graph for n is equal to 1, right? Very simple question, right? For n is equal to 2, how many graphs are there? For n is equal to 3, how many graphs are there? For n is equal to 4, how many graphs are there? So n is equal to 2, you can draw two vertex like this. One graph is this, G1, another graph is this, G2, right? If we are looking at simple graph, right? There are two. So the question is, given n, how many graphs are possible? Can you answer this question by your program? For given n, sometime you will observe that when you're doing this sort of classification, how many graphs are possible, sometime by rearrangement, of vertices and edges, you can convert one graph to the other graph. So they are kind of equivalent. So basically, you need to discard those equivalence things and find out uh, when two graphs are basically isomorphic. So that is very important thing, basically isomorphism of the graphs, and it's still an open problem. So people are looking for polynomial time algorithm for solving graph isomorphism problem. I'll tell you more details about this, graph isomorphism in coming lectures. It's a very interesting problem. It's still not solved, or one can look at quantum algorithms. So solving a polynomial time algorithm on a quantum computer to show that whether two graphs are isomorphic or not. I mean, that is one thing. So that is theoretical part. You show that when they are isomorphic or not. Other part, I'm asking how many graphs are there for given vertex. So this you can do by writing a computer program, right? So we need to capture certain things before we can actually talk about those things. So anyway, another theorem I would like to give you. A property, an undirected graph has even number of vertices of odd degrees. Undirected graph has even number of vertices of odd degree. Why is that? If V1 is set of vertices of even degree and V2 is set of vertices of odd degree, then by the previous theorem, 2 times E is equal to summation U belongs to V, degree of U. This I can expand it. U belongs to V1, degree of U, plus sigma U belongs to V2, degree of U. Okay. Now degree of U is even, this side is even. If this side is even, then that means what? The sum is even on the right hand side, right? Now V1 is set of, this whole thing is even actually. It's even. So I think from here you can clearly see that even number of vertices like this is even. All even. Okay. Anyway. Let me draw another graph. A, B, C, this, this, E, D, F. Every edge has a direction, right? A, B, C, D. This is E and F. Can you tell me what is minus means in degree of A? Degree means, this is coming here. Means how many arrows are coming towards A? 2. Very good. In degree of C. C is 2 or I think I drawn one picture here. Another one is there. 3. Very good. What is this? Outgoing. 2. Very good. What is this? Oh, sorry, I have written 0. Outgoing degree of A. 4. But this is something very common sense, right? I mean, these things are taught actually, right? So, I mean, you can find it out. So, even degree, out degree, in degree, out degree. So, this is known as in degree. How many arrows are coming and how many arrows are going, right? In degree and out degree of a vertex. In a directed graph, you can define like this, Okay, I can now talk about spatial graph known as complete graph. It is a simple graph that contains one edge, exactly one edge between each pair of vertices. So we denote it by Kn on n vertices. So this is your K1, K2. There are, one edge between two vertices. What will be K3? This, and this, K3. K4. Each edge, between any two vertices, there is one edge, right? And similarly, K5, you can find it out, something like complete graph are quite useful. I think we have used complete graph, a kind of modification of it for distributed storage in cloud computing. So sometime I can show you that how it works actually, So these graphs are quite useful, complete graphs are quite useful for a lot of applications as well. So cycles. Cn. So there is, n vertices and edges are like between 1 and 2, 2 and 3, and so on, n and 1. So cycle. C3. Okay. C4. T5, and so on. These are cycles, you know. What about, okay, we can also talk about wheels. So from cycles, so here we take this cycle here, C3, look at C3, and we add another vertex. Okay, this will be W3 now. We are converting from C3, and you add everything. This is from cycle, we can get wheel. Okay, similarly here, take the center and join everything here. This is V4, this is a wheel, right? Take the center and join everything. So from here, cycle, you can get wheel. From here, cycle, you can get wheel like this. All these kind of things are possible. Hypercube, you know already, right? Wheels I talked about, hypercube. Hypercube, a line contains only 2 points. A line contains only 2 points. A square contains only 4 points. 1 0, 1 1, 0 0, 0 1. And similarly, cube will have 8 points, right, in the space. That is hypercube. So we know that mathematically we can write down z2 raised to power n, x1, x2, xn, such that xi belongs to z2, right? This will have 2 raised to power n elements. In general, you can draw the cube. So from 3-dimensional cube, you can stretch to go to 4-dimensional cube. 4-dimensional cube can be stretched to form 5-dimensional cube, and I mean, for higher dimension cubes, that is possible. I think that's all. So I think that's all for today. I mean, we're not going to do. Now, next class, we will be looking at bipartite graph, which are also another important thing.